Hi student, in this module I will mainly talk about maximum likelihood estimation in R. I split maximum likelihood estimator into two modules. In the first module I will talk about how to use the optimum function to get the maximum likelihood estimate. Mainly I will start with how to define the log likelihood function, and then how to use that log likelihood function in the optimum function to get the estimate, and how to read the results that are there, and from there I will show you how to extract the standard error of the estimates and related inference from there. So in this module, as I told that we'll learn how to implement the log likelihood, the likelihood estimation, the maximum likelihood estimation in R. So let's start with the declaring the log likelihood functions in R. So estimating the log likelihood functions entails a two-step process. The first one declares the log likelihood function, which is done in general terms. Then one optimizes the log likelihood function, which is done in terms of a particular data set. The log likelihood function and optimization command may be typed interactively into R command window, and they may be contained in text file. Declaring the log likelihood function as follows. The log likelihood function is declared as R function. In R function, take at least two arguments. First, they require a vector of parameters. Second, they require at least one data object. Note that other arguments can be added to this if they are necessary. The data object is a generic placeholder for data. The optim command specific data are substituted for this placeholder. Consider the Poisson log likelihood function. Say Poisson dot likelihood equals to function mu is the parameter and y is for data. Two arguments, as I told, and then n equals to n row of y, and y is a data matrix. Then log likelihood is sum of y into log mu minus n into mu, and then we will return the negative log likelihood. So this is the log likelihood function. That's the way you should define the log likelihood function to use the optim function for maximization. The Poisson.link is the name of the log likelihood function, and this name will be used in the optim command, as I mentioned, and the vector of parameters is called mu. This is not really a vector, since there is only one parameter that needs to be estimated here. Further, y is the placeholder for the data. Since the log likelihood function requires knowledge of the sample size, we obtain this using n equals to n row of y, assuming y is a data matrix. The expression for log L contains the kernel of log likelihood function, and finally we return we ask R to return minus 1 times the log likelihood function, the negative log likelihood function. Imagine that let's use a normal example for illustration. Imagine that we have a sample that was drawn from a normal distribution with unknown mean mu and variance sigma square. The objective is to estimate these parameters. The main objective is to estimate these two parameters. The normal log likelihood function is given by L minus 0.5 into n ln 2 pi minus 0.5 ln sigma square minus 1 by 2 sigma square sum over I y minus mu whole square. So this is the log likelihood, and then we can program this as normal dot link 1 like 1, then function theta and y, mu equals to theta 1, sigma 2 equals to theta 2, then n equals to n row of y, and this is the log likelihood, and then return the negative log likelihood, just like Poisson function. Here theta is the vector containing two parameters of interest, and we declare the elements of this vector in first two lines of the bracket part of the program, and especially the first element, that is theta 1, is equal to mu, while the second element theta 2 is equal to sigma. The remainder of the program sets the sample size, specifies the log likelihood function, and ask R to return the negative of this function. Note that the normal log likelihood function may also be written as this: L equals to minus n L sigma plus I equals to 1 to n ln phi of Zi, where Zi is yi minus mu by sigma. This can be programmed using, say, normal dot like 2, this function theta y, as you mu is theta 1, sigma theta 2, n is n row of y. In Z we define y equals to minus mu by sigma, and log L is this expression, and return negative log likelihood. Then using optimization by optim function of the likelihood. Once the likelihood function has been declared, the optim command can be invoked. The minimal specification of this command is optim, then starting values, log likelihood, and data. Here the starting value is a vector of starting values, and log likelihood is the name of the log likelihood function that you seek to maximize, and data declares the data for the estimation. The specification causes R to use the Nelder algorithm by default. If you want to use BFGS algorithm, that is Newton method, you should include the method BFGS option, and for LBFGSB algorithm you should use within double quote L-BFGS-beta. The current specification does not produce the standard errors. A procedure for obtaining standard error will be discussed later in this module. So let's start with the example of Poisson distribution. Imagine that we have a vector data consists of a draws from a Poisson distribution with unknown parameter mu. We seek to estimate the parameter and have already declared the log likelihood function as Poisson.like, and the estimation using the BFGS algorithm now comments as follows. Say data equals to matrix, I just generate the data of lambda say 4.5, and total number of data point is 100, and you generate the data from R Poisson n equals to 100 and lambda equals to 4.5. So data is the data matrix, and then optim that one parameter, so the initial value we set as 1. Then the name of the log likelihood function is Poisson.like, then data y equals to data, and method is BFGS. So it will give you the estimate is 4.22. We assume 4.5, the estimate is giving 4.22. Increase the sample size, you will get the higher accuracy, and the log likelihood value is minus 1.85, the count 20, function 20, and the gradient value is 6, the convergence is 0, mass is null. So these are the output of optim functions. The estimate would be given. Given a vector of data, that y, the parameters of normal distribution can be estimated as follows. Say data, we are creating a data matrix and generated 1000 sample size from normal distribution with mean 45 and standard deviation 10. Then optim, see the two parameter of the initial value of the two parameters, say 25 and 5. And the normal dot like 1, y equals to data, method BFGS, then it will give you the estimate as 4.5 into 91.99, that is sigma square. So the square root would be almost approximately 10. The optim specification discussed so far will produce several pieces of output. These come under various headings. First, the pair, this shows the MLE of the parameters. Value, this shows the value of log likelihood at MLE. If the ask R to return minus 1 times of log likelihood function, then it is a value reported here. And the counts as a vector that reports the number of calls to the log likelihood function and the gradient. The convergence, a value of 0 indicates the normal convergence. If you see a 1 reported, this means that the iteration limit was exceeded. This limit is set to 10,000 by default. And message, this shows the warning of any problems that occur during optimization. Ideally, one would like to see null here, since this indicates that there is no warning. Now we learn how to obtain a standard error from there. The optim command allows one to compute the standard error based on observed Fisher information matrix. So, you have to extract the Fisher information or the Hessian matrix. To do so, what you have to do, you have to set Hessian equals to true or T or true within the optim function. Since we will have to perform operation on Hessian, it is also important that we store the results from estimates into an object. So, imagine that we are interested in estimating a simple linear regression for some simulated data. So, first we create the data matrix for the predictor, say x equals to c by n c are uniform 100. So, this is a data matrix, a simple linear regression, one for intercept and rest is for x, and here we draw 100 observations from a uniform distribution with 0 limit 0 to 1 for the actual variable, and these data are bounded together with a constant 1 as I mentioned. Next, we postulate a set of values for true parameters. Say theta equals to true is actually 2, 3 and 1, and then here the first element is beta naught, second element is beta 1 and the last element is sigma square. We can now create dependent variable, say y equals to x into theta dot true 1 to 2 plus r norm 100, where r norm 100 generates the disturbance by drawing 100 values from the standard normal distribution. We now have the data on dependent variable and predictor. So, the next step is to declare the log likelihood function. The following syntax shows how to do this. Say OLS dot LF is function theta y comma x, 3 arguments we are passing. So, n is in row of x, k is in column of x, then beta equals to theta 1 to k and sigma 2 equals to theta k plus 1, and then e equals to y minus x into beta, the x prime x beta actually. So, log likelihood is then minus 0.5 into n into log 2 pi minus 0.5 into n into log sigma 2 minus t transpose of e into e, that is e prime e, and 2 into sigma 2, and then return the negative log likelihood. So, return minus log L. Here theta contains both the element beta and sigma square. The program declared the first k element of the theta to be beta and k plus first element to be sigma square. The vector E contains the residuals and E prime E, that is trace of transpose of E into the matrix multiplication E in the log likelihood function causes R to compute the sum of square residuals. So, we can now start the optimization of log likelihood function and store the results in object name P. In this, any other name would have worked just as well. So, P equals to say optim, then the initial parameter said to be 111, then OLS LF, the log likelihood function, then method is again BFGS, Hessian is true, then y equals to 1, x equals to 2. It will actually generate the results along with the Hessian matrix. And then where 1 1 1 sets the starting value of beta naught, beta 1 and beta sigma square equals to 1, and we can now invert Hessian to obtain observed Fisher information matrix, and this Hessian is stored as P dollar Hessian. So, it can be inverted using solve command. That you have to take the inverse and say y is actually solve P dollar Hessian. The square root of the diagonal element are then the standard errors corresponding to beta naught, beta 1 and sigma at square respectively. These can be obtained by typing say standard error AC equals to square root of the diagonal of y. So, you have to get the diagonal elements of the y matrix, the Hessian matrix, and get the square root, you will get the standard error. You can type AC to get the standard error for all the 3 parameters for beta naught, it is 0.195174, for beta 1 it is 0.365341, and for beta sigma hat is 0.1512 as the standard error of the parameters. So as we get the standard error, so easily we can report the statistical test or the inferential part of the regression analysis. With the standard error in hand, wall test statistics and their associated p-value can be computed. The following syntax will accomplish this task for regression model of the example. Say t equals to p dollar PAR, where you have the estimate. So t equals to p dollar pair by standard error, that will give you the t statistics, and now you can calculate the p value by pt, the t distribution, that is 2 into 1 minus pt absolute value of t, comma n row equals to x minus the degrees of freedom is n row of x minus n row of a column, that is almost n minus 2 that we do, a number of columns that you have, n minus 3 actually, sorry. So the results equals to C bind B, that is beta equals to P dollar pair, that is the estimate in that particular list, and then standard error, then T statistics, and then P dot value that was calculated in the previous line. And then we will give the name of those rows as row names, results as C. First one is constant, second one is say x1, and the third one is the sigma, and then we can print the results up to 3 digit, and then that will give you this table of the regression analysis, where the first row will provide you the estimate of all the 3 parameters, say the beta naught, beta 1 and sigma square, and then standard error of them, that is beta 1 is 1.73, 3.61 for beta naught, and sigma square is 1.07, whereas standard error is 0.2, 0.365 and 0.15. T statistics was calculated, and that is the estimate divided by the standard error, that is 1.73 by 0.20, that would be your T statistics. So 8.866, 9.88 and 7.07, and all p values less than 0.001, so it's highly significant. So that's all about the implementation of maximum likelihood estimations through optim function in R. In the first module of MLE, we learn how to use the optim function to get the maximum likelihood estimate through defining the likelihood functions from the distribution or from the model, and how to read the data and how to extract the standard error from the data, that is through the Hessian matrix that we normally take. That we learn that the standard error can be extracted through the Hessian matrix at the final estimate, and the diagonal of that matrix, the square root of the diagonal of the matrix will give you the standard error of the estimates, and then how to use the standard error and the estimate to get the inferential statistics, say the test for all the parameters, how you need to test those, and how to get the 95% confidence interval from this. That also, though we didn't talk about much, but if you have the standard error and if you have the T statistics, easily you can get the 95% confidence interval too. So mainly we have, and finally we have seen that how to make the inferential conclusion, inferential statistics, or how to get the inferential statistics or the statistical analysis or final table that will provide you the estimate, standard error and the p-value of the t-test for the final outcome.